Good morning. Myself, Dr.CR Kesavulu, Associate Professor, Department of Physics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. So today I am going to discuss about the spectroscopic investigation of Nd3+doped Silicaborateglasses for NIR laser applications. This is the one of the important topic from the laser glass spectroscopy. So previous session we have discussed about all the visible laser applications. Today onwards we are going to discuss about the near infrared laser applications. This is one of the important topic from the laser glass spectroscopy. Next, previous and last session we discussed about the influence of erbium-3+ ions in concentration and spectroscopic properties of Silicaborateglasses. In that, we have discussed the introduction, experimental methods and techniques, results and discussion, and a summary or conclusion of the erbium-3+doped laser Silicaborateglasses. So today topic is the mainly spectroscopic investigation of Nd3+doped Silicaborateglasses for the near infrared laser applications. So outline of the today talk is on the introduction and experimental methods and techniques, results and discussion, and finally we are conclusion or summary of the Nd3+doped Silicaborateglasses. So main introduction or motivation of the rare earth elements. This is the modern periodic table. In this modern periodic table, we are going to discuss all the lanthanide doped ions. So particularly today we are going to discuss about the third element of the lanthanide ions or rare earth elements, neodymium. This is Nd3+doped Silicaborate laser glasses. So among the 14 elements, we are going to discuss about the Nd3+doped laser glasses. So this is what is the importance of lanthanide 3+ ions. Among the lanthanide ions or rare earth ions, in that we are going to discuss about the Nd3+ ions. So these are the what is the important properties or importance applications in the Ln3+doped laser glasses. So shielding of 4F orbital, because Nd3+doped glasses also its ground state is mainly belongs to the FF orbital. So that is a similar chemical properties and the electrostatic bonding and a variable geometry. These are the importance in the lanthanide or rare earth elements. What are the fascinating optical properties involved in the lanthanide doped laser glasses? So first is luminescence from the FF transition to F orbital transition. So FTF transition only here takes place because this is the black elements, and also characteristic emission of each rare earth ion and narrow emission line, high chromatographic purity, and the emission colors is not very dependent on the ion's environment, and large stroke shifts. So here in this laser glasses we can observe the large stroke shifts also. That is a blue shift or red shift. So based on the composition, we can study the stroke shifts also. Yes, direct excitation in 4F levels is not efficient. Sensitized luminescence is prepared. So finally, long excited state lifetime will be observed. So in the rare earth elements, we can dope with the rare earth elements, we can get the longer excited state lifetimes. That is decay times you can get in the order of milliseconds. So these are the blue to, that means visible to near infrared laser emissions. So previously we have discussed about all the visible emissions. So far we discussed samarium, europium, dysprosium, terbium. So thulium so far not discussed. These are the visible emissions. Today we are going to discuss about the last lesson we have discussed the erbium dope. That is erbium having a visible emission and as well as near infrared emission. This Nd, you cannot get any visible emission. You can get only in the near infrared laser emission. That is why Nd doped glasses used for the NIR laser applications. So this is one of the important topic in our laser glass spectroscopy. Let's come to the introduction. That is a rare earth elements. So 4F and 5F black elements, their unique trivalent state 4F and electronic configuration shielded by each and every rare earth elements, 5s2 and 5f6, 5p6 electrons, and so many advantages involved in the rare earth elements. Next, what is the importance of glasses? The glass is an indispensable photonic platform material due to its high optical transparency. So optically is a highly transparent in thermomechanical strength and the ability to be shaped into almost unlimited range of geometrical structure and composition. While changing the composition, we can prepare the different variety of laser glasses we can prepare by using the rare earth elements. So what are the important applications in the rare earth elements? Laser gain media, fiber amplifiers, optical components, medical accessories, and massive structure and entertainments. These are the different kind of applications involved in the rare earth doped laser glasses. Particularly rare earth elements in glasses. What kind of important parameter we can get? There is many applications. Importantly, we can discuss mainly laser gain media, optical fiber amplifiers. That means stimulated emission fraction should be more, and at the same time decay lifetime, that is the emission lifetime, will be more. These are the important parameter while observing the rare earth doped glasses. So these are the introduction involved in the today topic. Next, introduction. These rare earth doped glasses have been an increasing interest in the field of photonic applications. Such applications includes photoluminescence, up conversions. Up conversion is nothing but if down conversion means we are giving higher energy, we are getting lower energy. That is called down conversion. Up conversion means we are giving low energy. Pumping energy will be low, but output energy will be we are getting more. This kind of conversion is called up conversions. So laser emission and applications. These are the rare earth elements and important applications. Next, it is a powerful tool upon the usage of rare earth doped or lanthanum ions as structural probes in order to study the local fields surrounding in individual rare earth ion sites within the glass matrix. You have chosen glass matrix. Within the glass matrix, we can vary the rare earth element sites, and individual each and every rare earth ions exhibit the significant luminescence properties. That is why you can dope with different kind of rare earth elements. That is within the glass matrix, it can change the different properties. Among the different rare earth ions, neodymium ion is one of the most efficient ion used for prepare the solid state lasers because of its intense emission at 1060 nanometer. So usually Nd3+doped is give the near infrared emission, that near infrared emission at 1060 nanometer. Almost this is useful for the solid state laser applications because intense emission we can observing at 1060 nanometer. So in our present study we are observing 1059 nanometer. So this is one of the important laser system of the Nd3+doped with silica borate glasses. However, there is a less importance in these glasses due to their high photon energy. So actually, this borate glasses and silica borate glasses, that means you are mixing of some silicate is there. That is why photon energy will be a little bit high compared to borate glasses. So it is well known that the glassy systems with the low photon energies are highly suitable for the high efficiency lasers and fibers. So whenever we are choosing the worst material, low photon energy, that means whenever you are choosing the low photon energy materials, that is the highly suitable for the high efficiency lasers and optical fibers applications we can use for the Nd3+doped laser glasses. Next, coming to the material selection. In the present, material selection highlights the facts or advantages behind the selection of borate glass system. That is, in our present glass, we are using glass composition is silica borate glasses that also mixed with the gadolinium. So, spectroscopic investigation of Nd3+doped silica borate glasses for the NIR emission at 1059 nanometer, 1059 nanometers. So, chemical composition of Nd3+doped gadolinium calcium silica borate glass system composition is we are taking here 55 minus X boron trioxide B2O3 and 10 mole percentage of silicon dioxide and 25 mole percentage of gadolinium oxide Gd2O3 and 10 mole percent of calcium oxide and X mole percentage of Nd2O3, the neodymium oxide. So this neodymium oxide we are varying. This is dopant of the rare earth elements or lanthanum ions. So this is concentration starting from the low concentration to higher concentration. So here referred as BSGD calcium Nd 0. Low concentration and 0.05 and 0.5 and 1 mole 1.5 to 2.5. These are the different mole concentration of the Nd3+ ions doped in the gadolinium calcium silica borate glasses. So this is the our prepared glass sample. So how this glass sample prepared? So we are going to discuss in the experimental technique. The preparation of glasses we are prepared by the using the conventional melt quenching technique. Initially, you are taking the that above mentioned chemical compositions. We are taking 20 grams. The batch composition of the weight will be 20 grams. That will be weighing with using the optical balance. After taking the chemicals, we have put into the agate mortar. This agate mortar, we need to crush the powders from micro size to the nano size. We have to fine powder. We have to make it by using the agate mortar. After fine powder, granular powder, we can put into the platinum crucible and cover with a platinum lid. That completely the chemical composition keep into the platinum crucible. That will be your keep into the electrical furnace at the melting temperature of 1400 degrees centigrade. For time duration is 90 minutes. After melting the glass composition, we need to pour into the preheated brass mold. So preheated brass mold, we have to pour into the melted chemical composition. Then that will be kept at the annealing temperature at 460 degrees centigrade. The time duration is 5 hours. So that is we are keeping to the annealing furnace. So annealing furnace we are kept at 460 degrees centigrade for 5 hours. After cool down to the room temperature from 460 degrees centigrade to room temperature, then after taking to this glass sample to cut the required sample desired sizes and well polished in both sides, in the back, front and back, both sides we have to well polished with using some cerium powder. Then after that glass sample will be sent to the calibration purpose. So first initially we need to measure the XRD profile. This is important because we prepared glass sample will be whether it is shows the glassy nature or crystalline nature. Sometimes some glasses shows the crystalline nature. So to avoid the crystalline nature, we need to measure first initially. We have to whether it is a glassy nature or crystalline nature. So XRD profile we have to confirm. So in this XRD profile we are observing broad XRD peaks we are observing. That peaks indicates that so our prepared glass sample shows the completely glassy nature. So after taking the glass sample, we need to measure the different kind of calibrations. So this is the experimental technique or calibration methods. Initially, we need to measure first absorption spectra. So absorption spectra, we need to measure using the Flickr spectrometer by that model number is lambda 950 in the wavelength range of 250 to 2500 nanometer. Then fluorescence and decay time measurements we need to measure. In this, we need to measure NIR emission, where measure the FLS 980 spectrophlorometer. Yes, the NIR decay times is measured by using the 980 nanometer laser diode with frequency of 100 Hz directed with the indium gallium arsenide detector and a digital oscilloscope. So all the measurements were carried out at room temperature. So all the NIR emissions and NIR decay times, all measurements will be carried out at room temperature only. Next, coming to the optical absorption spectra of the Nd3+doped 0.1 molar Nd3+doped gadolinium calcium silicaborate glasses. So this figure shows the optical absorption spectra of the Nd3+doped glass. So wavelength versus absorption coefficient. We are observing the absorption peaks from visible region to near infrared region also. So here the ground state of Nd3+ ion is 4/9/2 different excited states. See figure shows the optical absorption spectra of the Nd3+doped gadolinium calcium silicaborate glasses ranges from 350 to 1000 nanometers. The assignments of the absorption bands is from 430 nanometer to 876 nanometer in the NIR region. So these are the transition from the ground state 4/9/2 different excited state, that is a 2p 1/2 and a 2g 9/2 and so on. Then finally we are getting 4f 3/2 transitions. These are the absorption transition from the ground state to different excited states. The band at 80040 nanometer is almost, so this is the 800 nanometer. This nanometer is most commonly used for the optical pumping of neodymium based lasers either by flash lamps or semiconductor gallium arsenide laser diodes. So 804 nanometer, this commercially we are using this 804 nanometer is the most commonly used for the optical pumping of neodymium based laser glasses either by flash lamp or by semiconductor diode laser, that is gallium arsenide laser diodes. So this is the important band for the pumping the Nd3+doped laser glasses. Next, coming to the optical absorption spectra, we have to calculate the judo of rate intensity parameters, that is the JO parameters. So JO intensity means judo of rate intensity parameters we have calculated by using the absorption spectra. In this absorption spectra, we have calculated the omega 2, omega 4, omega 6 values. In this present study, we observed the omega 2 value is 2.14 into 10 power of minus 20 centimeters square. Omega 4 is 2.57 into 10 power of minus 20 centimeters square. Omega 6 is 1.93 into 10 power of minus 26. Here order follows. Omega 4 is more. Omega 4 greater than 2. Omega 2 greater than 2. Omega 6. So this is the trend follows for the geo intensity parameters. So among the three intensity parameters, omega 4 is the maximum value you are observing, that is 2.57. So this larger value of omega 4 indicates the higher rigidity and higher covalence between the Nd3+ ions and its surrounding ligands, that is O2- ions. So this is the main indicates the larger value of omega 4 values. These are the comparing with different host materials. This table shows our present glass shows the omega 2, omega 4, omega 6 and the susceptibility value, that is 1.33. This is the quality factor. This quality factor is you are getting omega 4 by omega 6, that is 1.33. So this is useful for the laser transitions we can use for the quality factor. So these are the parameters where this is spectroscopic quality factor, that is the 1.33. This is one of the important parameter in the Nd3+doped Silicaborateglasses. Next, from the Nd3+doped glasses, we are observing the near infrared emission spectra. So near infrared emission spectra, we are pumping with the 808 nanometer and we are getting the emission channels, different emission channels. So here see the emission channels from port F 3/2 to port I 9/2, one emission. These are the all three emission bands in the near infrared region only. Just maximum intensity we are observing at port F 3/2 to port I 11/2, and small intensity emission is port F 3/2 to port I 13/2. Among the three transitions, we are observing the maximum transition is port F 3/2 to port I 11/2. This is the emission band is 1059 nanometer. Most commonly used Nd3+doped laser glasses is 1060 nanometer. This is commercially used. But in the present study, Nd3+doped Silicaborateglasses, we are getting laser emission at 1059 nanometer. Slightly 1 nanometer will decreasing the low level, that is 1059 nanometer. So in the emission spectra have been measured as a function of Nd3+ ion concentration. We are studying the different concentration from low concentration to higher concentration. That is low concentration is 0.5 to 2.5. So the Nd concentration by exciting 808 nanometer in the wavelength range from 830 nanometer to 1500 nanometer. The emission spectra exhibit the three emission bands. One is 903 nanometer, other one is 1059, and one is 1334 nanometer, corresponding to port F 3/2 different levels. So in this one, among the three transitions, we are observing maximum intensity is 1059 nanometer. This is highly useful laser glass spectroscopy in the NIR laser applications. This intensity of port F 3/2 to port I 11/2 transition increases with the increasing of the Nd3+. See the different concentration. From the increasing of the Nd3+ ion concentration up to 1 mole percentage, you will be increasing the luminescence, that means NIR emission intensity. After increasing the concentration, the NIR emission will be decreasing. That is increasing the Nd3+ concentration due to the enhancement of interaction between the excited state of Nd3+ ions and the ground state of Nd3+. This we can discuss in the energy level diagram. We can discuss in deeply in the energy level diagram, because lower level to excitation level. So the energy transfer between the ground state of Nd3+ ion to excited state of Nd3+. The through cross relaxation channels, we can get the energy transfer takes place. That is why increasing the concentration at the certain concentration, it will be increases. After that, it will be quenching. Quenching means decreasing the luminescence intensity. That is mainly due to the energy transfer between the lower energy of Nd3+ ions and the higher excited state of the Nd3+ ions. So this we can discuss in the next slides. Next, coming to the NIR emission, we can, by using the NIR emission, we can calculate the radiative transition probabilities. That is the AR value, branching ratio, and tau radiative value. So these are the important transition of the near infrared emission. That is port F 9/2, port F 5/2, port F 3/2. These are the important emission transitions. In particular levels, we are observing the radiative transition probability A value and branching ratio as well as tau radiative transition, radiative lifetime decay times in the microseconds. So at the quarter F 9/2 transition, we are getting 442 microseconds. In a quarter F 5/2 level, we are observing 482 microseconds. In quarter F 3/2 transition, we are observing 600 microseconds. These are the radiative decay lifetimes. So we can calculate the stimulated emission cross section also by using the emission spectra analysis. By using this formula, we can calculate the stimulated emission cross section. This is the one of the important laser parameters, stimulated emission cross. So which transition having the higher stimulated emission cross section, that laser, that kind of Aeronautical glasses is useful for the laser glass applications. So fluid width of maximum and branching laser, these are calculated from the NIR emission spectra. This is the table shows the emission peak wavelength lambda p and effective bandwidth delta effective nanometer and relative transition property AR, the branching ratio PR and stimulated emission cross section. So previously with this stimulated emission cross section, by using this formula only, we are calculating the sigma values. So these are the important transitions of the Nd3+doped gadolinium calcium silica borate, the quartile 9/2 transition. From the transition from quarter F 3/2 to quartile 9/2 transition, we are observing the stimulated emission cross section is 0.49 into 10⁻⁻20 centimeters square. Next, quartile 11/2 transition, we are observing 1.39 into 10⁻⁻20 centimeters square of the stimulated emission cross section. And quartile 13/2 0.3. Among the three transitions, we are observing the maximum stimulated emission cross section value is 1.39 into 10⁻⁻20 centimeters square. That is why this is the highly useful for the at the particular wavelength 1059 nanometer emission wavelength. It is suitable for the laser applications. You see, intense emission we are observing at 1059 nanometer, comparing with 903 and 1333 nanometers. Next, coming to this table shows the band position and delta effective and branching ratio and stimulated emission cross section and the figure of merit and tau radiative. These are this present glass we are getting at the particularly intense emission 1059. So remain commercially glasses and the LG L42, LG 650. These are the commercially prepared glasses. In our market available laser glasses. That laser glasses shows the wavelength emission, near infrared emission wavelength is 1065, 1056, 1059. So in our glass also we are getting 1059. See, this is a highly suitable for the LG 650 nanometer. That is the reference number 42. That both are the similar. In our present study 1059 and this LG 650 glass also exhibiting the highest intensity at the emission wavelength of 1059 nanometer. This is the highly useful for the near infrared laser applications, useful for the Nd3+doped Silicaborate glasses. Next, coming to the decay time measurements. So in our Nd3+doped gadolinium calcium silicaborate glasses, we observe the decay time measurements from the different concentrations, from low concentrations to high concentration. This figure shows the time versus normalized intensity. See here, we are taking the concentration from low concentration. This decay times we are pumping with 808 nanometer and emission monitoring emission at 1059, because we are among the three emission transitions, we are highest intensity we are observed at 1059 nanometer. So we are monitoring the emission wavelength at 1059 nanometer, pumping with 808 nanometer diode laser, that is semiconductor diode laser. So from port F 3/2, different decay times we are observing. So low concentration shows that is 0.05 concentration of Nd3+ shows the single exponential nature. There is no energy transfer observed in the low concentration because it shows exhibit the single exponential nature. So increasing the concentration from 0.5 and 1.0 and 2.0. These three concentrations shows the non-exponential nature because the energy transfer takes place from the concentration from 0.5 to 2 mole percentage. See the decay curves of port F 3/2 level have been measured by exciting the 808 nanometer and monitoring the emission at 1059 nanometer as shown in the figure. All the glasses NIR decay curves are exhibited non-exponential nature except low concentration of 0.0. This shows the single exponential nature for low concentration of 0.05 mole percent. Remaining all the other concentration will be exhibiting non-exponential nature. This non-exponential nature well fitted with the Innocuity Hirayama model. So that we will discuss in next slide. This lifetime measurements we are carried out by using the formula of tau experimental, integral of t into I of t dt by integral of I of t dt. By using this formula, we can calculate the average lifetime of the Nd3+doped Silicaborateglasses. So in this table shows the N0 concentration value, tau experimental value, and the Q value, R0, CDA. These are the energy transfer parameters. Q is the energy transfer parameter. R0 is the critical transfer distance, R0, that is angstroms. Next, CDA is the dipole-dipole interaction parameters. So this non-exponential nature is well fitted with the Innocuity Hirayama model, that is the IH model. That is, you can say Innocuity Hirayama model, IH model, by using the equation I of t equal I0 exponential minus t by tau naught. Tau naught is the lower concentration of decay lifetime of the Nd3+ science. Q is the energy transfer parameter, and S is the Innocuity Hirayama model. S equal 6. If it exhibits the S equal 6 means it shows the dipole-dipole nature. If S equal to 8, it shows the dipole and quadrupole. If S equal 10, if non-exponential nature fitted with S equal 10 means it shows the quadrupole nature. That is energy transfer parameter shows the different types. If S equal 6 means dipole. In our present study, it shows the S equal 6. That means dipole type. So here, that is why you are calculating the CDA value. That is dipole interaction parameter CDA. We are observing the present study 3.22 and 2.92 and 2.26. This is the dipole parameter value. By using the Innocuity Hirayama model, we are calculating the Q, energy transfer parameter. See, the energy transfer parameter increasing the concentration, the energy parameter also increasing from low concentration 0.43, 0.82 and 1.44. These are the increase in the Nd3+ concentration. Energy transfer parameter also increasing the concentration. This shows the energy transfer takes place at a higher concentration of Nd3+ science. So these values we are comparing with different host materials, bismuth silicate and fluorosilicate and different kind of other glass systems. Next, coming to the energy level diagram of the partial energy level diagram of Nd3+ science, Nd3+doped gadolinium calcium Silicaborateglasses. This is the energy level diagram of Nd3+ science. This is the ground state of quarter 9/2 of the Nd3+ science and different excited states from the ground state to excited state. See here, near infrared emission, we are working with 808 nanometer. We are observing the 3 emissions. One emission at 903 nanometer, other one is 1059, another one is 1334 nanometer. Among the 3 transitions, we are getting the 1059, the intense and highest intensity emission and prominent emission we are observing in the region of near infrared region. So that is why this is useful for the NIR laser applications. So in this one, we can observing the decay times are increasing, the concentration lifetime will be decreasing. That value here, that is mainly due to the cross relaxation channels. What are the cross relaxation channels we observed in the present study means quarter F, that means ground state levels from here to here, this level, and quarter F 3/2 to quarter F 15/2. These 2 levels and these 2 levels both are matching. Energy band gap will be matching together. That means this energy difference and this energy difference will be almost similar. That is why this takes place energy transfer from higher, that means excited state Nd3+ science to ground state of Nd3+. That is in here, see, this is the except and non-excited. This is the Q increasing the critical distance between the donor excited state Nd3+ science, see non-excited Nd3+ science, decreasing and increasing the Nd3+ science concentration, which clearly indicates enhanced energy transfer process between the Nd3+ science through one of the cross relaxation channel. So this cross relaxation channel, this 2 cross relaxation, any one of the will be exhibit. That is why energy transfer takes place from the excited state Nd3+ science, lower state Nd3+ science. So this is the partial energy level diagram of the Nd3+doped Silicaborateglass systems. Next, finally, conclusion or summary of the present study. The gadolinium calcium Silicaborateglasses doped with Nd3+ have been prepared and characterized structural, thermal and optical luminescence properties, and Judah-Flickr parameters have been used to predict the radiative properties of the luminescence levels of the gadolinium calcium Silicaborateglasses. The emission spectra of the present glasses showed strong near infrared emission at 105 nanometer, corresponding to the quarter F 3/2 to quarter F 11/2 transition, with stimulated emission cross section value is 1.39 into 10⁻⁻20 centimeters square, and the experimental branching ratio also 58%, and optical gain bandwidth is 45.73 into 10 power of minus 27 centimeter. These are the important laser parameters in the region of near infrared region of the 1059 nanometer. The decay times of the quarter of 9/2 level decreases with the increasing of Nd3+ concentration in the present classes. The exponential decay curves are well fitted with the Inocuity Hirayama model for S equals 6. That S equals 6 indicates the dipole type of the energy transfer parameter. So this is the energy transfer process through cross-reduction channel between the Nd3+ ions is a dipole nature in the present Nd3+doped gadolinium calcium silicaborate. Finally, hence the obtained results indicates that the present Nd3+doped gadolinium calcium silicaborateglasses could be applied suitable for the optical amplifiers as well as for the efficient NIR laser emission at particularly 1059 nanometer. That is why in our present study classes is useful for the near infrared laser applications. These are the conclusion or summary of the present Nd3+doped silicaborate glass systems. Next, these are the important references cited in the present study. So in this present study, this spectroscopic investigation of Nd3+doped silicaborateglasses in the NIR laser application. This paper was published in the Journal of Alloys and Compounds in the 2017. This is one of the important paper in the particular study. So these are the cited references in the present study. Thank you. Next class we will continue with the other elements. Thank you once again.
Like, share and subscribe. Hit the bell icon for more updates.